For example 5, again, we want to do some kind of substitution to be able to substitute into our defined g of x function. So our power series function, I'm just going to call g of x for now, is 1 over 1 minus x. And I want to be able to replace that x with some expression to generate the 1 minus x minus 3. Sorry, 1 over x minus 3. So there's some techniques to do this, but we could do this in a way where we can solve this. So we could say that if I substitute some value a into here, I'm going to end up with 3 minus x. So I just got to figure out what that a is. Okay, well, figuring out what a is solving. So I end up with 1, and then we're going to subtract 3 plus x on both sides. I'm going to add a to both sides, so there's my a value. Okay, so I can say that a is the a that I want to replace into that expression is going to be x minus 2. So that's what I'm going to do. I'm going to plug that into that x there, and I'm going to generate my f of x. So my f of x then, that 1 over 3 minus x, can be done by embedding into g the x minus 2. And by doing so, I'm going to end up with 1 over 1 minus x minus 2. Okay, now you don't need to do this formally, you just have to figure out what's going in there. But once we set that up, now we can write our power series. 1 plus x minus 2 plus x minus 2 squared plus x minus 2 to the power 4 plus dot 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 dot. And I'm just going to put the x minus 2 where the x was originally in the power series. Okay? And if I graph this, graphing this with the first 5 terms, so if I graphed it all the way up to x minus 2 to the power 4, I'm going to get this purple graph here. And that purple graph is the power series that approximates that function 1 over 1 over 3 plus x. Okay, so the function that's being graphed in red here is that function. It's got a horizontal vertical asymptote at x equals 3, and you can see that it's centered at x equals 2. Okay, where the center of this is what we're going to call the center of convergence, and it looks like it's converging, up to maybe 1 and maybe up to about 3 or so, and that is what we call our interval of convergence. Okay, and that's going to be determined by when this series is going to converge. That series is going to converge when the x minus 2 is going to be between, that's the term that is going to be the base of the function, where that's going to be between negative 1 and 1. And if I solve for x, I'm going to add 2 to both sides. We can see that that's how we get our interval of convergence between 1 and 3. And we can see that when we sketch that graph. This is a sketch that you should see. Make sure you draw this in your notes. And we can see that it converges. The interval of convergence looks like it's converging up to about up to 1. After 1 to the left, it's diverging. I'm just going to highlight, notice that it's diverging here compared to that. And after 1 is definitely diverging after 3 it's definitely diverging because it's on the other side of the x-axis. So it's definitely diverging on the right side of 3. So this is what we're going to start calling the interval of convergence. We're slowly introducing some new terms. Okay, that becomes what we call the interval of convergence. And again, I want you to notice that the more terms we use, in this case, I use the first 5 terms. Okay, well, in this case, the first 5 terms goes up to power 5. Okay, and let's skip, it's going to go up to power 3, sorry, power 4. I just need to fix my notes here because that should have been power 3. Okay, and again, use one more term. And when I graph that, I get this purple graph in here, which converges between 1 and 3, but it diverges outside of that because that series will no longer converge.